Hello everyone. So in this video, we will continue talking about simple linear regression. We will focus on inferences on parameters. Okay, remember, so for parameters in linear regression, we have beta 0 and beta 1. Again, just remember, please, previously we were talking about parameters mu and sigma. And what we do is we just use confidence intervals, right? Let me just write it here. Confidence intervals and hypothesis testing for parameters mu and sigma. We will do the same thing for beta 0 and beta 1. Remember how we constructed confidence intervals or how we established hypothesis testing on mu? We just use X bar, right? And how about sigma? We just use S. And remember, these were the point estimators of mu and sigma. Similarly, for beta 0, we will just use B0. For beta 1, we would use B1 to make confidence intervals or hypothesis tests for the parameters. So let's remember, we said that, well, this is the population regression line, right? Beta 0 plus beta 1 xi plus epsilon I. So any observation that you have is equal to the mean. Remember, this was the mean, right? This is the constant mu given xi, right? And plus the error term. Remember, this was the error term which is normally distributed with 0 and with standard deviation or with variance sigma squared. Well, the fitted value, how we find the fitted value? Well, we just estimate the parameters b0 and b1. Then what we do is just substitute xi to this line equation and find the predicted value yi hat. So what is yi hat? Yi hat, remember, is the x bar of what? Mu y given xi. Okay. So this is mu, we want to estimate mu, and this is the estimator of this mu. And the thing is that for anybody, for example, let's assume I'm just talking about a guy whose height is 163 centimeters. What we do is we just plug this into this formula and find yi hat, right? And we said that, well, this is the estimator of this guy. So for any guys whose height is 163 centimeters, it will give the same prediction, right? And okay, so this is my ith response, right? So this is yi equal to b0 plus b1xi plus ei. Remember, we said that, well, b0 is the estimator of beta 0, b1 is the estimator of beta 1, and ei mimics the random variables epsilon I. I cannot observe epsilon I because I don't know beta 0 and beta 1, but I can observe ei because I estimate b0 and b1, find the estimator from here, and the difference is ei, right? So ei is equal to yi minus b0 plus b1 xi, which is yi hat. So this is my error term. So the error term is the difference between the observed value, the observed value and the predicted value. And what we do is, remember, we just sum the error squares, right? The error squares, yi minus yi hat or yi minus b0, you can just write it like this. b1xi squared, and we just minimize this. Find the b0 and b1 that minimizes the sum of squares, right? And there were formulas which are I don't memorize them, but just for b0, right? b0, what was it? It was something like y bar minus z b1 times x bar. That's something like this. I don't know it by heart, so I don't expect you to know it by heart. So, okay, this is our model, the regression model, and remember we have some assumptions for the terms epsilon i's. We said that, well, they are independent random variables with mean zero and constant variance. So independent, in fact, normal random variables, right? Normal random variables. And these are the formulas to find B1 and B0, right? This is the formula for B0, so I was right. And this is the formula for B1. Again, B0 is the estimate for beta 0, and B1 is the estimate for beta 1. So what we do, what are the steps in regression analysis? So what we do is we just first look at the data, right? The x's and the y's, and using the formula above, right? We just find, sorry, this is B0 and B1, not B1 and B2. Okay. So we say this is B0 and B1. We just find B0 and B1 using the formulas above. So we just estimate, in fact. By estimating B0 and B1 means we just estimate linear relationship between Y and X, because we just estimate the line. This line, that's great. So this is the first step, okay? But the thing is that, well, so just go back. Just look at here. What you do here is that xi minus x bar, yi minus y bar, xi minus x bar squared. So for any given set of numbers, any given set of x and y's, so for example, assume that you have something like this. You have data like this, right? See, so is there any linear relationship here? Well, no. So, but if you just put the data here to the columns here, so this is, let's say this is X, this is the first data, this is the second data, this is the third data. So, if you just put the data here, right? So this is the first X. So this is the first data, X1. So look at it. So this is X1. This is the second data, X2, Y2. That I don't know. This is the 52th data, 52nd data. This is the 52nd data, right? If you just put them here and then put the data to these formulas, you will find values for B1 and B0. So what I mean is these formulas do not look and check whether there is a really linear relationship between the data. So if you just put any values to this column and this column, it will give you a value for B1 and B0. But this does not mean, this does not assure that there is a linear relationship between the data between y and x. Okay? So what we do is, so first we just find b0 and b1, okay? And then we just check our assumptions. What are the assumptions? Remember, first, there is a linear relationship between y and x. Second, epsilon is a normal random variable between 0 and variance sigma, and so on and so forth. How do we check our assumptions? By just analyzing the residues. Well, we will do it later in the next chapter in the multiple linear regression case. Okay? So in the third step, what we do is we just draw inferences about model parameters, beta 0 and beta 1, by using hypothesis tests and confidence intervals on the parameters. Then, if we feel confident enough, if we feel that, well, our model is right, our assumptions are valid, then we just make predictions. What do we mean? For example, in our height and weight example, for given any weight, we just build confidence intervals on mu r given xi. So for example, we will just build confidence intervals for guys whose height is, for example, 68 centimeters. We will just build confidence intervals on this. And we will just build prediction intervals on this, okay? So remember the difference between the confidence interval and the prediction interval. So this one is the confidence interval is for the mean, and prediction interval was for a single observation, okay, for a single guy. So we will make these predictions. Okay, so this is the fourth step that we will do in regression analysis. Right? So, well, okay. So again, just go back. Well, we said that we will deal with the second one in the next chapter. So we will. And we know how to estimate the B0 and B1, we have the formulas. Now we will check the third step, where we just draw inferences about the model parameters. Okay, so in order to make inferences, remember, for mu, we just draw inferences using x bar. Okay, that's great. But so remember how we just make this. We just use the distribution of x bar. How we said that, well, this is central limit theorem, and we said x bar minus mu divided by sigma over root n, or then we just say x bar minus mu divided by s over root n. We say that this is normally distributed and this is a t distributed, and we just make our inferences over the parameter. Okay? So we will do the same thing here. Well, it turns out that we can show b1 and b0 are normal random variables. How? Under the assumption that epsilons are normal and there's a relationship between y and x and so on and so forth. So under the assumptions, we can say that b0 and b1 are normal random variables. So what does this mean? Normal random variables mean that, well, you can say b1 minus mu of b1 divided by sigma of b1, right? So this is what? This is standard normal, right? This is standard normal. No, yes, this is standard normal. What does it mean? With mean 0 and with standard deviation 1. This is how this random variable is distributed. Similarly, you can say b0 minus mu of b0, right, divided by sigma of b0 is, okay, so again, b0 minus mu of b0 divided by sigma of b0, that's normal with 0 and 1. So as you might guess, we don't know sigma of b0 and we don't know sigma of b1, right? So what we do is we will just replace them with s of b1 and replace this with s of b0 and say that, well, then it will be t distributed, right? T distributed. Okay, so let's check what is the expected value of b0 and b1. Well, it turns out that the expected value of b1 is beta 1. Expected value of b0 is beta 0. So remember, what does this mean? It means that, well, so B1 is an unbiased estimator of beta 1 and B0 is an unbiased estimator of beta 0. Again, given that the assumptions are correct. So under the assumptions, so what were the assumptions? Epsilons are normally distributed with 0 and 1, with 0 and sigma square, and they are independent, and there's a linear relationship between y and x. Under these assumptions, it turns out that B1 and B0 are unbiased estimators of beta 0 and beta. Okay, then what are the standard deviations or the variances? It turns out that the variance of B1 is sigma square. So what is the sigma square? This is the sigma square of epsilon. Okay, divided by xi minus x bar squared. And variance of B0 is sigma square, right, times from 1 to n xi squared divided by n times xi x bar squared. So this is the variance of B0 and this is the variance of B1. But again, do we know sigma squares? No. So what we do is, instead of sigma squared, we will again estimate this using s squared. So how to estimate this s squared? That's the question. And if we are able to estimate s squared, then we can just put it here and estimate the variance of B0 and B1, right? And then use this formulas here. Right? Well, just small notations in order to just make the formulas easy to check. So this is Sxx. What is Sxx? Xi minus x bar squared, and we just sum it from 1 to n. Syy, yi minus y bar squared from 1 to n. And as xy, right, xi minus x bar times yi minus y bar, right? This is Sxy. If you just use this notation, well, it's easy to show that B1 is equal to Sxy divided by Sxx. And remember, B0 was simple. It's equal to y bar minus B1 times x bar. Okay. Well, then you can show that, well, the sum of squares SSE is equal to Syy minus B1 times Sxy. Okay. So these are just small notations. We didn't do anything new. Right? So what we do is we just define new notations, and using these notations, we just rewrite SSC and B1, B0 and B1. Now, the theorem says that an unbiased estimate of sigma square, remember what was sigma square? It was the standard deviation of epsilon, right? And why do we need this? We need this because we need to find S of B0 and we need to find S of B1. Why? Because we will make confidence intervals and hypothesis tests for what? For beta 0 and beta 1. That's why we need an estimate of sigma square. So S squared, which is the unbiased estimate of sigma square, is equal to SSE divided by n minus 2. What was SSE? SSE is equal to summation from 1 to n yi minus yi hat squared, okay? Divided by n minus 2. And instead of this SSE, we just plug in this, okay, and divide it by n minus 2. Okay. So let's think about this a little bit. So remember the original S square where we don't have any linear regression. It was equal to summation yi minus what? Y bar square. Remember? Or in fact, we didn't use yi and y. We just used x there. Okay, so that's not a big deal. Instead of x, I'm just using y as the variable name. Yi minus y bar divided by n minus 1. Okay, so remember what was this? This was the unbiased estimator of sigma square, which we call the sample variance. How do we calculate the sample variance? What we do is we just take the difference between the observations and their average and square them and divide it by almost to n, not exactly n, but almost n, right? Why? Because remember, this is what? This is, so yi minus y bar, that's the error term, or that's the deviation around the mean. That's the difference of yi, okay, and the mean. So this difference, we just square them and sum them up. So this is in fact the total, what? This is the total difference or the total deviation, let's say, around what? Around the mean, right? This is the total difference or total deviation around the mean, okay? And what we do is we just divide it by n minus 1, almost n, let's say, to find the deviation, right? The deviation per observation, okay? Per observation, right? Now, let's look at our case. So, in fact, the total difference or total deviation, the definition for the total deviation is just take the difference between the average and the observed value, okay, the average and the observed value, and square it and sum them up. So just look at here. Again, just think about the definition. Take the difference between observation and the average. So what is our average now? Well, the thing is that we don't have a constant average just like this, y bar. So our average is depending on xi's, okay? So at different values of xi's, we have different values of averages. And it is shown by yi hat, okay? So in fact, this is the average of this observation. Okay, so this is the average, this is the predicted average of this observation, right? So in the previous example, in where we don't have any regression there, the average was constant, okay, it's y bar. But here, the average at every observation, the average depends on xi. So at every average, we have a different, a different estimator for the average, which is yi. So in fact, what we do here is the same thing. Just take the difference between the observed value, okay, and the predicted average, and square them and sum them up, right? And this is, let me just change the color so that it doesn't get very confusing. So this is what? This is the total deviation, right? This is the total deviation. Okay? divided by now it's n minus 2. Why n minus 1 and 1 n minus 2? Okay, just come here. This is n minus 1 because here, well, in fact, what I'm trying to do is I'm trying to find the deviation around the average, but I don't know the average, hence I just um, I just estimate the average using X bar or here Y bar, okay, Y bar. So what I do is I just make a single prediction. That's why I have a minus 1 here. Now just look at here, this is a minus 2. Why? Because I predict two things. The first one is B0 or beta 0, right? And the second one is beta 1. So I just predict two things here, okay? That's why I'm just writing n minus 2. So in the next chapter in multiple linear regression, we will see that we will just predict more than two parameters, then we will have n minus 3 or 4 and so on and so forth. Okay. Okay. So we will continue in the next video for the inferences about B1.